the recording started? Yes. And I will share my screen. Okay, so what we are planning to do today is application of concepts of norms, distance, and similarity. Do you want to say something, Yogesh? I think it is very difficult for me to keep track of chat.
Sir, can you please discuss something regarding affine function, like some example real life application in ML? Uh,
Yeah. So that you will see in assignment that you're supposed to submit. That is not a very difficult thing. So I don't want to discuss. I'll give that in assignment. After that also, if you feel you want to discuss it, I will discuss it. No problem.
yes, sir. Yes, sir. Okay.
So this is something that we want to discuss, the application of concepts of distance and similarity. So what happens really in any AI ML application is that there are certain objects. So the task is that there are certain objects, certain collection of objects is being given. And what we want to do, we want to put similar objects in one class. So that's what we want to do. So this problem arises almost everywhere, right? This problem you have been facing for a long time since you started doing things. So for example, the problem might be you go to a hospital, and then in a hospital, similar patients are supposed to get similar type of treatment. So you like to club the similar patients together. Or a couple of examples that we have already seen from vectors is that there are documents, and you will like to put similar documents in one group. So for example, if you are given 100 documents and there are like 10 main areas in those 100 documents, so you will like to put them in 10 different areas, like documents related to sports, document related to medicine, document related to engineering, so on and so forth, right? So that is something that we want to do. So this is a very natural problem that arises, and this problem needs to be addressed. And how do we do that? So that's what we are going to do. So there are a couple of things that are there. So the first thing is collection of objects is given. So this object can be anything. We want to find out a linear algebra equivalent of these objects. So the linear algebra equivalent of these objects is going to be feature vector. Okay, so what we mean by objects as far as our course is concerned, so by objects we mean vectors or feature vectors belonging to Rn. That's what we mean. And what do we mean by similar objects? Similar objects, we mean collection of vectors which are close. Okay. And when we say close, or yes, Atif, do you want to say something?
Sir, there are few people who are waiting as guests to join from the PhD group.
Oh, I think yesterday I made a thing. I will not be required to give permission. Everybody will get in straight away.
I don't know, sir. Like they are posting that they are not able to get into the class.
Can you ask them to put a request again? Here I don't see anybody waiting in the guest room. I get a message and I generally accept. But
Sir, actually, there are three meetings going on simultaneously.
there?
There are three meetings going on simultaneously.
No, why
So
three
might
meetings?
be, I don't know, sir, but there are, I can see.
I don't know. I clicked on the same meeting. The only thing is that I log in from two devices, one from my iPad and one from my laptop. And I use calendar to log into the meeting. So I don't know why two meetings are same meeting I have logged in. I can see about about
So they are
nine.
saying that, sir, they're saying that you're not there in the meeting itself. So I guess they are in some other
Then
meeting.
they are
So
Yes.
probably going
ask
to
them to
small
join
meeting.
the meeting where there are already plus 98 people being shown in the. So just ask them to request in that way.
Sir, ask them
By
to
the
join
number
in the
of people,
meeting one.
they can understand which meeting is the right one.
No, but the link that I shared for the PhD students, was it different than the meeting that is going on right now? I think
I
I don't know because this is the meeting which I shared from the calendar, and I think how did Atif find this meeting? Atif,
Sir, I joined via the official channel.
official channel meaning?
Sir, many of them has joined that Wednesday's meeting. You have already.
So Wednesday meeting is no longer active now. No, this is Thursday meeting. So we have to join in Thursday meeting. Am I in Thursday's meeting? I think I am in Thursday's meeting, right?
But
Yes,
many
sir.
of them has joined.
No, no, no. So if you can inform them that they're supposed to join in Thursday's meeting, this meeting, not the other meeting, you please tell them they can log in. If I see anybody in the waiting room, they can join. Okay, I will allow them. So let's get back to this collection of vectors which are closed. Okay, so what is the collection of vectors that are closed? So close meaning some distance concept or some similarity concept has to come into the picture. Okay, so similarity will be in terms of distance and distance will be in terms of norm that we have already defined. So what distance I am talking of depends on different applications that I am talking. Right? So two important things that we have to understand. So whenever we say objects, for us in linear algebra, objects will be same as uh, vectors, and similarity will be quantified in terms of distance. Okay. So this is what we will have. So if we understand this, then we will see what we are going to do. So with this understanding, let me introduce some notation. So let us start with some notation. So the groups are going to be called as clusters. Okay, so the groups are going to be called as clusters. So this is a clustering problem, and if you have little bit of background in AI/ML, then this will be a clustering problem which is unsupervised. Okay, so this is unsupervised clustering problem, or sometimes it will be semi-supervised clustering problem. So we will come to this terminology little later. Right now, we will just say that this is unsupervised or semi-supervised clustering problem. So for example, what I will do is suppose there are x1, x2 up to xn. Okay, these are the vectors. Okay, so let me use a different n. So x1, x2 up to xn are the vectors in Rn. So there are n vectors, capital N number of them, And what is happening? So this is generally called as data. So there are many names. So one is objects, one is data. For us in linear algebra, they are vectors of size n, length n. And what I am going to do, I am going to have a vector c associated with this vector. So I will have numbers c1, c2 up to cn. So these are numbers. And what are these numbers going to tell? The cluster assignment. Okay, the numbers which is telling me cluster assignment. So suppose I have vector x1.
Sir, the number of classes is equal to the size of the vectors.
Can you ask again?
Number of clusters is equal to the size.
No, number of classes is not equal to size of the vectors. I am explaining that. So suppose x1, x2, xn are the n vectors that we have. So this is the data. So this is the data or vectors that we have. Then this there are total 5 clusters. Okay, suppose there are total 5 clusters. Then what are these Ci? So Ci can take any value between 1 to up to 5 for any I is equal to 1 to up to n. So it will tell us what are the cluster assignments. So this vector C is helping me with cluster assignments. So for example, if I have n is equal to 6, then I have x1, x2, x3, x4, x5 and x6. And my CIs will be, so suppose this belongs to cluster 3, this belongs to cluster 2, this belongs to cluster 3, this belongs to 1, this belongs to 4. Oh, okay, so this was a bad choice of having 5 clusters. Let's say I have only 3 clusters. So if I have 3 clusters only, then this is 1, this is 2, this is 1. So that's my cluster assignment. So this is my C1, this is my C2, this is my C3, this is my C4, this is my C5, and this is my C6. Okay, so this is what I mean by CIs, cluster assignments. So CIs are telling me cluster assignments. And what are the clusters? So clusters is G1. So G1 will be equal to the first cluster. So there are how many in cluster 1? So 4 and 5. Vector 4 and 5 are in cluster 1. G2, how many are in 2? So in 2 there are x2 and x5. And how many are in G3? So there is 1 and 3, right? So this is what the clusters are. So G1, G2, G3 are clusters. So these are the clusters. These give me cluster assignment.
The clusters should be x4, x5, x1, x3.
Yeah, we can have x4, x5, or we can have 4, 5. That's why I wrote both the notations here. It's up to you. You decide what notation you want to use, and based on that notation, it's variable. People use varying notations. So that's why I wrote both. You can use any. That's not a big deal. And this is the data that is given to us. Data, vectors, or feature vectors. Okay. So that's what we have. Okay, and then what we want is something which is called as cluster representative. So this cluster representative or group representative is a vector. So that is something that I will define. So suppose there are n vectors, k number of clusters. So there is a reason why I am taking k as number of vectors. It will become little clear. So maybe this is where you cannot see what I am writing. So I'll write down again. So there are n clusters. N data points and k clusters. K clusters Then Z1, Z2, so let Z1, Z2 up to Zk are the cluster representatives. Okay, cluster representatives. So there are a lot of terminology introduction going on. So please be with me. This is not a difficult thing, but if you understand this terminology, then it becomes clear. Okay, so Z1, Z2, Zk are cluster representatives. Then what we want is that each representative. So how are these representatives to be chosen? These are chosen such that representatives are close to the vector, are close to the vectors in a cluster. Correct? So what we really have, so when we say closeness, the closeness is related to something which is a distance. So what we do is we say distance. So suppose you look at the ith vector, then Zi minus Zci. So this distance should be small. This distance should be as small as possible, or this should be very small. So let me write down once again so that
Sir, what is ZCI? It should be ZI.
x1 are the given vectors. C1, C2 up to Cn are the cluster assignments, right?
Sir,
Yes, 1 minute. Let me complete and then you can ask me doubt. So these CIs, C1 up to Cn, they will take values between 1 to up to k, because there are k clusters that we have decided. So in the cluster assignment, this C1, C2, Cn can take only these values, and you have Z1, Z2 up to Zk cluster representatives. Okay, cluster representatives. So these cluster representatives are also vectors of the same size as given vectors. So they are vectors in Rn. And ZCI, so ZCI, so Ci takes one of the values 1 to up to k. So if Xi is a vector which is having cluster assignment Ci, that means is one of the clusters 1 to up to k, then Z1, Z2 up to Zk, you choose that representative. So how do you choose that representative? By this ZCI, and you look at the distance of the vector Xi from ZCI, and what you want that this distance be as small as possible. Now, what are the doubts?
sir, is the cluster representative of a particular cluster? Is the part of that cluster, or it's just a
No,
general
it
vector?
cannot be part of that cluster. So we will see that the way we are going to find out the cluster representative, it will almost always be not part of the given data set, but it doesn't matter. So it can be part of given data set, it may not be part of given data set. The algorithm that we are going to see today will be such that mostly these will not be part of the given data set. Cluster representatives may not be part of given data set, but they all belong to this Rn.
So I have a question.
Yeah.
So X, all the vectors, the cluster assignment to the vectors and the cluster representation, they all come under, they all are the part of set R, right? The space,
What
vector
set?
space.
They are all of what set?
They all are the part, this vectors, cluster assignment and cluster representation. So cluster assignment is formed of vectors, group of vectors. Am I correct or not?
Cluster assignment is C1 is one of the numbers. So if you see this slide once again, then suppose there are three vectors. So suppose there are three clusters, then Ci will take one of the three values, 1, 2 or 3. So for example, if x1 is in cluster 3, then C1 is equal to 3. You see this.
Oh, okay.
C1 is equal to 3. If x2 is a vector which is in cluster 2, then C2 is equal to 2. So this one corresponds to data point 1, this 2 corresponds to data point 2, this 3 corresponds to data point 3, this 4 corresponds to data point 4, and the value of C1, C2, C3, C4, C5, C6 is one of the three values 1, 2, 3, which will tell what cluster. Okay.
Okay. Okay.
So that's what this is.
Sir, in that example,
Yes.
What are cluster representatives?
So we'll come to that. So cluster representative is given a cluster, you want to represent the entire cluster with only one vector. So that cluster might have 100 data points, but you want to represent the entire cluster with only one representative, not the 100 data points. That's what you mean by cluster representative.
Okay.
So is that clear?
So why is
Yes.
the subscript CI chosen for the ZCI?
What subset?
So subscript, I'm saying ZCI, no, in the next slide, in the cluster last line, you have written ZCI belongs to RM. Why ZCI
Yeah, so
you have written?
CI. So CI basically is one of the entries you can see here. CI is one of the entries 1, 2, 3 up to K, right? There are total K number of clusters. I want to say XI. So for that I, there is this I subscript of C, that is the connection. So what is the cluster assignment of XI? That is given by CI. So CI is, for example, 3. Then what is the representative of third cluster? That is Z3. So how do you know what is Z3? Z3 is ZCI.
Then it should have written Z3 only. ZC, because I varies from 1 to N, right? There are not
I
N
varies
clusters.
from 1 to capital N. That's right.
So then if I write like ZCI, if I expand it for I equal to 1 to N, then it becomes ZC1, ZC2, ZCN.
Correct.
But it should be ideally ZC1, ZC2 up to ZC.
No, but C1, C2, Cn are not entire 1 to capital N. No, they are only 1 to K. That's why I am having Ci, not I.
One more question following the same what he asked is that you said that for each vector you are doing a cluster assignment, right? From
Yeah.
C1 to Cn with
Yeah.
respect to the vectors xn, x1 to xn. And then just beneath that you have written C1 to Cn, which can, where n can go from 1 to k. So like when you define, like, this is cluster assignment is just one entity for each vector, right? One C1 can have just one vector, can represent just
C1
one
is
vector,
not a
that is
vector. Please understand, C1 is not a vector. C1 is a number between 1 to K. C1 is not a vector.
C1, but C1 represents, like, in this cluster assignment, you have assigned x1 to C1 cluster, right?
C1 is not the cluster. C1 is only a number. What is the value of C1? That is the cluster. C1 is not the cluster. C1 is only a number. C1 will be equal to 2. Then you will say that x1 is assigned to cluster 2, not C1. The value of C1 is the cluster assignment.
Sir, can we think C1 as some sort of weightage assigned to?
No. It is not that difficult there. You don't worry about it. It's very simple. You take n is equal to 100. You take k is equal to 5. Then what is the list that you have? You have list x1, x2, so on, so forth up to x100. Then I have C1, C2 up to C100. C1 can take value 1. C2 can take value 5. C3 can take value 1 again. So C1 and C3 can be same. There is no problem about it, right? So what is the value of Ci? That value is the cluster that is vector xi assigned to. So that's why I am always saying xi, Ci, so that I and I are together. And what is the representative? Representative is ZCI. So what is the value of Ci? Value of Ci is 1. So if Ci is equal to 1, then ZCI is same as Z1. So Xi, the ith vector, is represented by the vector Z1. That is the vector representation of the cluster. That's all I'm saying. I'm not saying anything more than that.
Sir, so basically what you are doing is you like in a graph there are 4 clusters present. So you are finding a cluster representative of a particular cluster. So
Yeah.
can you just explain why have you just taken that the cluster
I'm
representative would
just
be Z minus?
introducing the notation. I'm just introducing the notation. I have not told how to choose the cluster representatives. I have not told how to do the cluster assignment. I have not done anything of that. I'm just introducing the notation. I just want to formulate the problem first. And once the problem is formulated, then we will talk about how the values of Ci are decided, how the number of clusters is decided, how do you choose a cluster representative. They will all come little later, not now. I'm just introducing the notation here. I just want you to understand notation. That's all.
So
Okay.
C1, so the cluster, for example, C1 has value 1. C1 has a value assigned 1. Then C1 can also have like 1 to like can have multiple values as well.
No.
Okay.
How can you assign one
Actually,
vector to
give the cluster different symbol like A, B, C, or something like that.
what is it?
The C1, C2 that you are assigning the value now,
Yeah.
1 to 5.
Yeah.
Give them another name like A, B, C, D.
No. This is the best. This is the best notation that you can have, because this is the notation which will help you write a very efficient program. If you start thinking it in terms of programming, this is the best notation that is possible. This is how you would write a program. So this is the notation that you have to understand. This is not a difficult notation.
Okay.
This is a very straightforward notation. You have to think about it. That's all. That's okay. If you don't appreciate it right away, that's fine. You can think about it. Okay, that's fine. That's fine.
Is there any book with a reference where this kind of
I already told
notation
in the first class. The book by Stephen Boyd. You can read the book by Stephen Boyd, chapter 4. That this is from chapter 4 of Stephen Boyd's book. So this is what we have, and what is the clustering objective? Okay, so these are few terminologies. So the last of them is clustering objective. So what is happening in clustering objective? So I will call clustering objective JClust to be this: distance of x1 minus zc1 square plus xn minus zcn whole square divided by capital N. So what am I looking at? I'm looking at sum of squares, mean sum of squares. I'm looking at mean sum of squares of distances of individual vectors from the cluster representatives. So what is it that I'm really looking at? So you think of it pictorially. Okay, so I will draw a picture. So there are certain data points in R2. So the vectors are in R2, for example. So these are the data points that are given to us. Okay. So roughly there are 3 clusters that you can see. So C1, so K is equal to 3. Suppose N is equal to 100. So there are 100 vectors that I have here, 100 data points that I have here. So this is what I have. So I will use a different color for different data points here. And this is the third point here. So these are the data sets. So suppose these 3 colors together, N is equal to 200. And I, for some reason, know that there are 3 clusters available. So this vector, for example, is x1. This vector is x2. This vector is x3. This vector is x4. This vector is x5. This vector is x6. This vector is x7. This vector is xz, and so on and so forth. That is what we have as vectors. So suppose this vector is x100. Because there are 3 groups, k is equal to 3, what I have is 3 represented: z1, Z2, Z3, three cluster representatives. Okay, cluster representatives. Right? And all this C1, C2 up to C100, the cluster assignment can take values between these three numbers 1, 2, 3. That is what will happen. So this is what I have. And once I have this part, then what happens? I have this vector x1. So this vector x1, I assign cluster 6. So that cluster assignment is C1. So C1 can be equal to one of the three values 1, 2, 3. Okay, so let us say in this particular case C1 is equal to 1. Then what is the representative? The representative is ZC1, which is nothing but Z1. That's the representative that I have. Then you look at the vector x2. For x2, you have this cluster assignment C2, which is equal to 1 again. And what is the representative? The representative is ZC2 is equal to 1 because C2 is equal to 1. So ZC2 is Z1. Then you look at the vector x3. So x3, I have cluster assignment C3, which is equal to 1. So ZC3 is actually equal to Z1.
Sir, for x2,
So
C2
now
will
you
be
understand the notation? Do you understand the notation? What is happening?
C2 will be 2, right?
C2 will be 2. Yeah, it is cluster.
ZC2 will be yeah.
Sorry, C2 will be 2. Suppose I assign it in cluster 2, then it will be C2 is equal to 2 and you have ZC2 is equal to Z2 and so on and so on. That's the assignment that I do. Okay.
Yes, sir. It's clear now.
Yeah, and now you understand why this notation is the best notation, and I don't want to use ABC as cluster numbers and so on and so forth, because this is the best possible way, easiest way in which you can write the program. Okay, that's why this is happening. And now I will use a pink color and a cross to represent a vector which I declare to be the representative vector of each of the groups. So this cross is say Z1, this cross is say Z2, and this cross is say Z3. Then what am I really looking at? I am looking at the distances. What are the distances? So I am looking at x1 minus ZC1 norm, which is nothing but distance of x1 from its representative. So that ZC1 is Z1. I am looking at this x2 minus ZC2. That's what I am doing. So this is what I am looking at. This is x3 minus ZC3. This is what I am looking at. So these are the distances that I am really looking at. And what is my objective? My objective is that this particular distance be as small as possible if I am assigning x1 to cluster 1. This distance be as small as possible if I am assigning S2 to cluster C2, X3 to cluster C3, and so on and so forth. So that's what I am really looking at. So in this representation, with this understanding of notation, now I write this thing again. So I write this thing again, J clust. So what is J clust? So J clust is norm of x1 minus ZC1 whole square plus x2 minus ZC2 whole square plus so on so forth plus xn minus ZCn whole square divided by n. So this is nothing but mean square distances of vectors or data points from their cluster representatives. And now what will you want? Now what you want is you want this C1, C2, Cn assignment to be done in such a way, and to find out these representatives Z1, ZC1, ZC2 up to ZCn in such a way that this cluster representation is as small as possible. So once again, look at it. This cluster representation, so this objective, this cluster objective is basically sum of squares. So this J cluster is sum of squares. So it is always going to be greater than or equal to 0. The best possible scenario, the minimum value for this is actually equal to 0. So if you can find out this ZC1, ZC2 up to ZCN in such a way that this value is equal to 0. So when will this value be equal to 0? The value of this will be equal to 0 if you have k clusters. So C1 take values between 1 to 3 up to 3. And each of these vectors, when you do the cluster assignment, they actually coincide with the cluster representative. So what you really mean is that you don't have capital N number of distinct data points. You have only k number of distinct data points, which are actually your clusters. So this is like the most ideal situation that you could have thought of. So that is what you have. In practice, in real life situation, that is not what you will obtain. So in this particular diagram, all the black dots, all these black dots actually fall onto this pink cross. All these red dots fall onto this pink cross, and all the green dots fall onto this pink cross. And if that happens, then you see this object, the cluster objective JClust will have all these values to be equal to 0 plus 0 plus 0 plus 0 plus 0 divided by n, which is equal to 0. The best possible scenario. But what it means to say that these black dots coincide with the cross. That means that x1 is same as x4 is same as x5, x3 is same as x8 is equal to x5. They're all same as this pink cross. Then all these red vectors x2 and so on and so forth, they're initially to start with are same as this red cross. And same x7, x6, they are all same as this. So there are really only 3 distinct clusters. So that's what you have. This is the most idealistic situation that you can think of, which will not be the case in real life. In real life, you will not have this possible. In real life, you will have tightly knit clusters possibly. So all of them represented by a cluster representative, and you want that the distance of all these different data points in that particular cluster be as small as possible, right? So that is something that you want to do. So that's the cluster objective. So this clustering objective is to minimize this J cluster. Clustering objective is to minimize J cluster. And why is this J cluster changing its value? So you understand this J cluster. So this J cluster is a function of several things. It is function of first K. How many number of clusters?
Sir?
Okay, so this is the first variable here. The second variable is C1 up to Cn assignment. So what values C1, C2 up to Cn will take? So that is another variable. So C1 can take now values between 1 to k. What value should C1 assume? C2 can take values up to 1 to k. What value C2 should assume? In other words, what cluster assignment you will do to vector x1, what cluster assignment you will do to x2 will determine a different value of J cluster. And the third thing is actually ZC1 up to ZC. So Z1 up to ZK I will use. So this Z1 up to ZK, the choice of cluster representatives. Okay, choice of cluster representatives. So these are the 3 variables that we have to come into the picture. So these 3 variables will determine different values of the J cluster, and you have to choose that combination of the values of K, C1 up to Cn and Z1 up to Zk such that you will minimize this J cluster. So that's the problem that we want to solve. So if that is the problem that we want to solve, that problem will call as clustering problem. Is the whole picture clear what we are really going to do here?
Yes, sir, I have a question here.
Yes.
So, like, our objective is to minimize the J cluster that value.
Yeah.
So, in the base case, it becomes 0. So, if we increase the K, like K equals to N, so like each point is a different group. So, in that case, also the J cluster will be 0. But the group will be very loose now in that case.
But from your point of application, do you think you are solving this problem?
No, like it will not solve the problem. Like if we are assigning.
then you should not do that. So if you take C1 up to Cn, so there are capital N number of data points. You say there are capital N number of clusters, each cluster being the data point itself. That's fine. Mathematically, it is correct. But are you solving your problem? So this K should be as small as possible, right?
Yeah.
K should be smaller than N. If K is equal to N, then there is nothing to do. But at the same time, you are not solving the problem, right?
Yeah, but it will give the J cluster as 0. It is not solving the problem. Yeah.
Mathematically fine, but practically does that make any sense?
No, it is not doing anything. Yeah.
Look at this example that we saw. Clearly there are 3 clusters. You could go on with number of clusters is equal to 100 and you could make that J cluster to be equal to 0. Then you will say that your algorithm is saying there are 100 clusters in this data set. Do you think this is a useful solution to anybody?
No, like it will not be useful.
Mathematically it is correct, but practically it may be useful. You are right. So we have to have that K to be as small as possible. The number of clusters should be as small as possible.
Sir, if we consider an example like if we take x1, x2 to be coordinates of points in R2, then cluster representatives will also be a coordinate means point.
Correct. Correct. So I already told you here somewhere that this ZCIs will also be vectors in Rn.
Yeah.
So these data points are in Rn. The representatives are also in Rn. So for example, in this case, if you want, you can draw a coordinate axis like this. Then each vector here is actually the coordinate vector of a point. And then these crosses, which are nothing but the vector group representatives, cluster representatives, they are also vectors, coordinates of the representative. You are absolutely right.
Okay.
So can I make this hypothesis that the more we increase K, the less J cluster cost will be?
It may not be always true. May not be always true. So there are many interesting things in this optimization algorithm happening at a time. So it may not always be true.
Okay.
Sir?
Yes?
Why have we created a cluster representative in every cluster? Like our computer can do computations from every data point now. So basically, why are we doing this in practical?
I did not understand. Why are we what?
Sir, why are we creating a cluster representative in every cluster? Our computer can do the computations from every data point, no? Whatever we want. So why are we creating a representative of a particular group?
If you don't create a representative for a particular group, then what will you do?
Yeah.
No, you can do something. I'm not saying you cannot do, but what will you do? Right now, the way I'm posing the problem is in this particular manner.
Yeah. Yes, sir.
Is that clear?
Yes, sir.
Okay.
Sir, is it
Actually, even
possible for the
computer programs
clusters to overlap?
Sorry, what is it?
Is it possible for the clusters to overlap on each other?
Okay. So if I understand you correctly by overlap, if you mean, so for example, if you see this particular point x4, okay, this particular point x4, then roughly the distance of this point x4 from this representative looks to be same as distance from this point from this representative, okay, roughly. So you are not sure where to assign this x4. So if this distance, these two distances were exactly same, so this distance is d1 and this distance is d2, and if d1 is actually equal to d2, then you don't know where to assign this x4, right? You can assign it to cluster 1 or you can assign it to cluster 2. So by that, if you mean overlap, yes, then there might be some overlap like this, and then you make a decision, okay, some rule you will decide, okay, so if that happens, then I'll assign it to cluster 1 always, not to cluster 2. something like that. So that is an ad hoc rule. It may not be the best possible rule, but you will make such a rule and then you will try to avoid the overlap. So,
but the minimization objective will in this particular example, no, in the previous, go to the figure please. The minimization objective will always assign it to the x1, right? Sorry, z1.
No, I did not get the minimization objective.
No, if we fulfill the minimization objective, that
Yes.
will make that ZC1 will be in the for that exception point, right? Please go to the previous figure, the point which is overlapping, right? That will assign it to the closest cluster representative always.
Yeah, that is true. But if such a scenario happens that after choice of ZC1 and ZC2, X4 is the point which is equidistant from ZC1 and ZC2 both, what will you do? You have to do a cluster assignment, right? There are multiple solutions to C1 and C2 now. So what solution you will take? Probably that's the question he asked. That's what I understood by the question. So that you have to make an ad hoc decision, because both are feasible solutions, both are acceptable solutions. Now X4 can belong to cluster 1 and cluster 2.
If they are equidistant, but if it is closer to Z1, then the assignment will always be Z1 if we fulfill our clustering objective.
No. In this particular diagram, it is coming to be D1 equal to D2. In this particular diagram, that's okay. If you see that if I drew X4 like this, little bit away, that's my point X4.
Then the choice could be anyone, right? Then
now D1 is equal to D2. So I'm considering this case. D1 is equal to D2. Then what will you do?
Yes, this is understood.
Is that okay?
Yes, this is understood.
Okay, fine. So the optimal clustering, is something.
Hello, sir.
And you have suboptimal clustering. So there are two things that are going on here: optimal clustering and suboptimal clustering. So the optimal clustering is a clustering where you are sure that by appropriately choosing K, C1 up to C capital N and Z1 up to ZK by an appropriate choice, you are able to minimize it. Okay, so the cost function, the objective function JClust is minimized after appropriately choosing all these independent variables or the decision variables in the optimization problem, right? So you want to minimize this. So JClust to be minimized, that's minimize JClust. And what are the decision variables? The decision variables are star. Okay. But every time the optimization problem
sorry, didn't follow what is star.
So you're not able to see this? Sorry.
No, what is star? So star means all of them.
All of them, equation number. Star is all of them. So all these variables. Okay. So
for a given K we are minimizing, right?
What is that?
Are we minimizing for a given value of K? Because otherwise it will always be 0. We can always make it 0.
What is the value of K? We don't know. We'll just assume that K is less than N, and we don't know what.
K equal to N. I mean, like K coinciding with every point coinciding with ZK will actually be the minimum cost. So why?
No, so I put a constraint here. K is less than N.
Oh, okay. Sorry, I did. Sorry.
No. There is a lag. So I say it first and it comes little later. So that's why you are not seeing it. So K is less than N. I put a constraint. So once that is the situation, then you want to minimize. Every time it may not be possible to exactly minimize. You are not sure whether you have achieved the minimum or not, but you are reasonably happy with the result for the particular application that you are working with, and you stop there. you don't really worry about you have achieved exact minimum or not. The mathematical objective is to achieve exact minimum, but in reality you will not really worry about whether you achieve exact minimum or not, as far as you are satisfied with the result that you see after performing all these exercise of choice of K, C1 up to Cn and Z1 up to Zk. Okay, so once you do that, then you are happy, you stop there. That is suboptimal clustering. Okay, so in almost all real life applications, you will stop at suboptimal clustering. You will not really worry about whether you achieve your optimal clustering or not. You are happy with suboptimal clustering. Why that will happen and how those things really come into picture depends on how you choose those K, C1, C2 up to Cn and Z1, Z2 up to Zk. Okay, so this is the clustering problem and this is the clustering objective. And in this framework, now we want to understand how to make the choice of these three different decision variables. How many number of clusters? What is the optimal cluster assignment? And what is the optimal choice of cluster representative? These are the three things that we want to study. So that is something that we will do in tomorrow's class. So for today's class, this is what I want.
What is suboptimal clustering?
Suboptimal clustering is you want to minimize this cost function jclust, right? And how can you optimize this cost function jclust? So this optimization cost function jclust, the clustering objective, is a function of three different types of decision variables. What are they? The first is K. So that K is telling you how many number of clusters are there. The second is C1, C2 up to Cn. So that is telling you how to do the cluster assignment for each data point or each vector. And the third is Z1, Z2 up to Zk, how to choose the cluster representative. So these are the three variables. These are the three things that you can vary. And for each different value of this K, C1, C2, Cn and Z1, Z2, Zk, you will get a different value of Z cluster. Right, so these variables are called as decision variables, and jclust is called as cost function. And what you want to do is you want to find out the minimum value of the cost function by varying these decision variables. That's a typical optimization problem. It may be really difficult to vary all these variables K, C1, C2, Cn and Z1, Z2, Zk for all the possible values that they take. It might be very difficult. Computationally might be very hard. And practically may not be necessary because you can stop before that if you see the results are satisfactory. That's what almost always people do. And that's why you never get optimal clustering, which is exact minimum value, but you get suboptimal clustering where you are happy with the value which might be close to the minimum value but may not be exact minimum value. But the results are satisfactory as long as the application.
So how do we know that the value is close to the minimum value if we don't know the minimum value itself?
See, all these things you will not know a priori. That is the challenge. If you already knew the minimum value, why will you worry about the value which is not minimum value? So
exactly.
all these things are not known a priori. It is the decision is based on the application that you are working with. So I will tell you some examples. There will be some assignment problems that will be required to solve, and there you will understand what is suboptimal, what is optimal first hand by actually writing a code and actually doing clustering on your own. So you will get an assignment next week where you will be required to do all these things. So there all this terminology will become even clearer when you actually perform the task on your own. Okay, that is something that you have to do on your own to realize. So this is something that cannot be explained just like that in the class.
Okay.
Is this clear? So this is the clustering problem, and how to make an optimal choice we will see in tomorrow's class. So is there anything that you want to add to what we have done today? I know the notation might be overwhelming a bit, but it is not really. You have to be a little patient. You will understand.
So this formulation.
Yes.
Go ahead.
One question. Sir, previously one student was saying that about cluster representatives, that if we don't take cluster representatives, then how we can do clustering. Sir, what if we just find out all the distance from all points with all other points and then use...
Yeah, you can do that. I'm not saying you cannot do that. But the way I am doing clustering in this particular application is in this way. That's what I'm saying.
Understood.
See, you can do clustering by not choosing a cluster representative, but by dividing the data sets into two halves. So you can put a straight line between the two data sets, and that straight line divides data set into two parts, and those are the two clusters. I need not require cluster representative, right? So this is like clustering by hyperplane. So you have to come up with a hyperplane which will separate data points into two clusters. If the data sets cannot be linearly separated, then you have to come up with a non-linear surface which will separate data points into two clusters. So that's the basic idea behind support vector machine and so on and so forth, right? So you divide the entire space into different blocks, and one block means one cluster. So all the data points coming into that block, that is one cluster. That's how you can do without choice of cluster representative. You can do that, but I am not going to do that just right now. Okay, so that's what I'm saying.
Okay, thank you.
Sir, can you go to the previous slide for where you computed the Z1, Z2 up to Zk?
Here?
Yes, sir. So basically for a particular cluster, you are taking that there should be a point named as cluster representative whose distance should be minimum from every respective point of that cluster. So am I computing the distance from every point, or I am just considering that the distance of that point from every other point and the summation of that should be minimum?
No, I said x1 minus zc1 should be as small as possible. So zc1 has so zc1 has three possible values, z1, z2, z3. So I want to choose the closest or the nearest neighbor among the representatives for x1. So whoever is the nearest neighbor, I will assign that cluster. That's what I will do tomorrow. So what you are asking me basically is what I want to do tomorrow. So you can sort of wait until tomorrow and see what I do.
Yes, sir. Okay, sir. Yes.
So in this formulation, the distance you have used is Euclidean distance, right? In the
so
J
that
cluster.
Is the key. No, that is the key. You can choose any distance of your choice. Right
so
now,
can I say this that
invariably when we speak of distance, we think of Euclidean distance, but there will be a second assignment problem where you will have to do where you will have to work with some data set which is documents data set, and there you will try to do this with cosine similarity or the cosine distance that we introduced. So in lecture 5, I think I have talked about angles between the vectors, and using angles you can define the distance between the vectors. So you can use that similarity, that definition of distance, and using that definition of distance you can actually so that's what I'm saying. Similarity is quantified by distance. What distance you take is to be decided based on the application with which you are working. How do you decide that? It comes with experience. Nobody can tell you like this example.
As a general formulation of clustering, the other part of the formulation remains same. The objective remains same, right? Only the distance.
Yes.
Distance function changes.
Yes, absolutely. The objective J-clust will remain same, but the way you define J-clust, the norm definition will change in this first equation on this slide. You are right.
Okay,
Z is the mean of the cluster, right?
It will be mean of the cluster, yes. If you take Euclidean distance, then it will be mean of the cluster, yes. So that is what I will talk tomorrow. So two of you asked questions and already gave the answers about what is the optimal assignment and what is the optimal choice of cluster representative. That's what we will do tomorrow, and that will tell us that what we are really doing. So yeah, you are right. So is what we did today clear? Hopefully, you go back and look at these things again. Look at the notations once again. It might be a little overwhelming at first, but if you see, the concept is not really very difficult. Concept is really very easy. So please have a look at these things, and in tomorrow's class, this is what we will continue with. Okay, so tomorrow 9 to 11 we'll start at 9 o'clock. I'll send the meeting request, and I hope all the guys who are waiting in the guest room were admitted eventually. So please use the calendar. Okay, please use the calendar to join the meeting. I'm using calendar to join the meeting. So thank you very much for attending today's class.